All right, class, in today's lesson, we're going to talk about graphs of functions, which is found in section 1.2, part 2. Our objectives are to determine relative maximum and relative minimum values of functions, to identify and graph step functions and other piecewise determined functions or defined functions, and to identify even and odd functions. All right, so as an example, during the 2000s, the sales of bowling equipment in the U.S. increased and then decreased according to the model below, where C is the sales of the bowling equipment in millions of dollars and T represents the year, with T equaling 8 corresponding to 2008. According to this model, during which years were bowling equipment sales increasing, and obviously where were they decreasing, and then approximate the maximum amount of bowling equipment sales between 2008 and 2016. Okay, so in order to do this this problem effectively, you may need to use a graphing calculator. Desmos.com is also kind of effective, but to get the true sense of the problem, you'll want a graphing calculator. So what we're going to do is we're going to go ahead and type in this function. So go to your y equals on your calculator and type in 0.165 t cubed. T in our case can be x on the calculator, doesn't matter. Use the caret symbol to be able to do cubed, minus 7.16 x squared, or t squared, plus 100.6 t, or x in the calculator, and then minus 303.1, and then graph it. Now, if you are in a standard window, you're not going to be able to see your entire graph, so I'm going to give you a window to use. And that window that you should use is for x min. I want you to use the value 7 for x max. I want you to use the value 17 for y min. I want you to use the value 100, and for y max, use the value 180. All right, so if you go to your window and you change those values, so 7 for x min, 17 for x max, 100 for y min, and 180 for y max, and if we graph that, then we'll see this nice pretty parabola. Or something like a parabola. And so what it looks like is something that kind of goes like this. All right, so what we will say, and we need to use like the second trace function on our calculator. So, and we're testing the years from 2008 to 2016. So the way to do this, once you see your graph, is you're going to press the second trace, which is really calc, and then you're going to go over to value. And what we're going to do is we're just going to simply input 8, 9, 10, 11, 12, 13, 14, 15, 16 to see what these numbers actually are along this axis, okay? So if I go to second trace value and I type in the number 8, I will get 127, so about here. The output is 127.94. I'll just say 127. If I do that again for second trace value and I go to 9, I get about 142, so it's still increasing. If I type in 10, so second trace value 10, my value is 151. So it's still increasing. Second trace value, that was 10, so let's do 11 now. That's 156, so it's still increasing. Go ahead again, second trace value 12 this time, sorry. That value is 158, so it's still technically increasing. Second trace value, this time we're going to type in 13. And this time it's finally starting to decrease. So at 13 is where I finally start to get 157. Okay. Second trace value 14. 14 is 154. second trace value, if I put in 15, I get 151, so it's still decreasing. Second trace value, if I type in 16, I get 149. So this entire time, it was decreasing. So what is the increasing? It is increasing from 2008 to technically, if 2013 is the value that it decreases at, actually, let's see something. Okay, so what I want to mention is 13 is where we see that it starts to decrease, but it actually starts decreasing before 13 at 12, because for example, if you put in second trace value and you type in 12.5, which is between 12 and 13, you'll get a number that has already begun to decrease. So we're going to say it increases from 2008 to 2012. And then from there, it decreases from, from 2012 to 2016. Okay. Then it asks us what is the maximum amount of bowling sales between 2008 and 2016. So remember, to find the maximum, we go to second trace. We go to maximum, which is the fourth one down. And we're just going to do left bound and right bound of where we think that maximum is. And we know it was somewhere around 13, but we're just going to double check as far as the x value. So just press enter somewhere on the left. Move your cursor to the right until you possibly even see it start going down, and then guess by pressing enter again. And your maximum amount of sales, remember your y value is your sales, so we're actually looking for the y value at our max, and our maximum sales is about $158 million. Okay, so we've answered those three. We answered the increasing, we answered the decreasing, and there's our max sales. All right, on example 8, we are going to sketch this graph that we have below. It's a piecewise function. So what I want us to practice doing when we do a piecewise function is to start with the endpoint that we've been given, and then from there, we plot points or try to find the slope from there. This is linear, so we should be able to count slope from where we are. When they may be a different type of function, like a squared function or a cube function, you may want to test other points. But for now, we're going to do it this way. So for this first function, we need to focus on the end point. And this end section right here is less than or equal to 1. So that means we are going to have a closed dot for that endpoint. Looking at the next one, I see x is greater than 1. So if it's greater than 1, then that means that that endpoint is going to be an open dot. All right, so when we graph, let's first start by figuring out, well, what is the value if I type this in my actual function. So, for example, my test point for this one will be 1. So I'm going to test the value 1, okay, into my function here. Okay, so that's going to be 2 times 1 plus 3. 2 times 1 is 2 plus 3 gives me 5. So I should be able to put a closed dot at 1, 5. So at 1, 5, I should put a closed dot. Let's practice with the endpoints for now. I'll come back to how to actually get the rest of the lines. All right, the second point I'm going to test is also 1, in the second equation, but this one is going to have an open dot on it. So I'm also going to test 1, and that's going to look like negative parentheses 1 plus 4. Negative 1 plus 4 is 3. So that value with an open dot should be 1, 3. So at 1, 3, I'm going to place an open dot for that function. Okay, going back to our top function, our red function, notice that it is less than or equal to. So the way my graph should go, it should go to the left of where it's currently plotted. So count your slope. If the slope is 2, instead of going up 2 to the right 1, okay, we're instead going to go down 2 to the right 1 and plot a point. Down 2 to the right 1 and plot a point. And these are just like your tiny points to help you graph. Down 2 to the right 1, plot a point, and then we create a straight line. Okay, that's this part of my piecewise function. Now the blue line, notice it is greater than 1, so we're going to only choose to graph on the right side of that function, or the right side of that value. So noticing its function says -1, so that usually means down 1, right 1, down 1, right 1, correct? So that's exactly what we're going to do. We're going to go down 1 and right 1, plot a point, down 1 and right 1, plot a point, down 1 and right 1, plot a point. So that function goes this way. And we are now done plotting our piecewise function. Okay, even and odd function. So it says a function whose graph is symmetric with respect to the y-axis is an even function. A function whose graph is symmetric with respect to the origin is an odd function. Then it goes on to say that the graph of a non-zero function cannot be symmetric with respect to the x-axis. So again, it's even if it's symmetric to the y-axis, meaning I can kind of spin it around this way, right? If it's odd, it is symmetric to the origin, which means it spins kind of diagonally. But something that is considered neither technically is symmetric across the origin, across the x-axis, okay? Alrighty. And the way we test that is what you see at the bottom. Look at the very bottom. How do you test it? It says a function f is even for each x in the domain if you substitute in a negative value of the function and it's still positive, or it's still the original function, then it's even. If I put in a negative version of it's an input and I get a negative response of my original answer, then it's odd. Okay, so let's try that. So the first one, it says, is the function even, odd, or neither? So graphically, this graph looks like this. It's the absolute value function. And the way I can tell that it's symmetric is I can tell that it's symmetric about the y-axis. Like if I spin it around the y-axis, it's symmetric about the y-axis. So remember, if it's symmetric about the y-axis, then it is an even function based off of the notes from before. Now, to practice it algebraically, because not everyone's going to do a graph, to practice it algebraically, what they're saying is substitute a negative x into our function. If when I substitute a negative x into my function and my answer is still the exact same as it was before I even tried to mess with it, then it's even. If I put a negative into that function and it changes to the opposite form of what it is, then it becomes an odd function. So for example, if our original function is f of x equals the absolute value of x, and I now want to input negative x, what happens to our function? Well, let's see. The absolute value of a negative x, well, the absolute value of anything negative, okay, sorry, I don't know. I think that was a school drill. Anyway, if you substitute in negative x, okay, so the absolute value of negative x is anything, if you put inside an absolute value, it will become positive, so this is positive x. And that is still reflective of our original. So this, again, is still even. All right, so for try 9, what we're going to do is we're going to determine whether each function is even, odd, or neither. Remember, if you substitute in a negative value and you get the exact same answer as before, then it is considered an even function. If I substitute in this negative value and I get the exact opposite, meaning opposite signs, then it's odd. If I substitute in a negative value and it's a mixture of both sets, then that's considered neither. So again, if I test this, g of x, or g of negative x, sorry, equals negative x cubed minus a negative x. That's going to give us a negative cubed is still negative, so that's still negative x cubed. And a double negative here gives us a positive x. This function here is the exact opposite of our original. So that means that this is an odd function. Whoops. Excuse the handwriting. Okay, the next one, h of x, or specifically negative x, h of negative x would be negative x squared plus 1. A negative squared would make it positive, so this becomes positive x squared plus 1. Now, this looks the exact same as what we tested originally, so this one is an even function. And on the last one, if I test using a negative x, I'm going to have negative x cubed minus 1. And what this will give me again is a negative cubed is still negative, so this would be negative x cubed and then minus 1. This first piece, though opposite, the second piece is the same. So this is considered neither. All right, guys, that is it for this lesson. If you have any questions, please come see me.